I mean,
Well, all right. Can we try again? I see some green light here. Can you hear me? Can I just get a quick confirmation from folks on? Yes, wonderful. Thank you. Well, thanks for letting us know earlier than later. This is good. All right. So as I was mentioning, this was made possible via NASA Wide Field Science grants. So and here's a few other missions that my group Astromusers is currently focusing on. I just want to highlight, before I start to talk about Roman, I just want to highlight ultrasat and access that some of you may not already know. And maybe towards the end, if I have time, I will just show one slide on access as we just got selected for phase A. And Tess, I'm pretty sure you all know. And Roman, we will use this colloquium to talk about. So let me first set the stage by arguing that dark matter in the universe is essentially a compelling observational finding that has evidence across many independent probes across cosmology and galactic astrophysics. Historically, the problem came out of the rotation curves, but soon after, it was confirmed is also in other galaxies, as well as through essentially strong lensing on the left-hand side, left button, 1979 detection that you see over there. We confirmed the requirement for dark matter, additional dark matter essentially that does not gravitationally interact or otherwise produce visible light in the form of additional mass in these lensing galaxies. We obtained further evidence for dark matter through n-body cosmological simulations from a theoretical side. And around the same time, 1980s, as you may know, there was essentially a phase in particle physics where people argued that there must be beyond standard model particles that can indicate or that can act as a dark matter particle. So from multiple directions, there is theoretical and observational evidence for the existence of dark matter. Most recently, we had a few very interesting signals. At the top right, for example, you see essentially a baryonic component that is spatially separated from a non-baryonic component that is traced through, again, gravitational lensing. And at the bottom, you see the Planck two-dimensional surface brightness of the cosmological microwave background, which again, I don't have time to go into, but the peaks, the amplitudes and shape of the CMB spectrum require that there be a non-interacting component, mass component in the universe at around redshift of 1,000. Without that, we cannot produce the structure that we see around the amount and richness of structure that we see around us today. And one signal that I worked on that is relevant to this was the gamma ray GeV access at the Galactic Center. This was my first PhD project, which continues to excite us, although there is an alternative, potentially alternative explanation from extended millisecond pulsars. So while such anomalies continue to exist and excite us, we are also trying to look for additional and independent observational evidence methods to search for astrophysical signatures of dark matter. I want to remind you that there are multiple ways to search for dark matter. If you're a particle accelerator, you can accelerate particles, collide them in controlled experimental setups that we call particle detectors. That's called production method, or you can otherwise take a slab of mass that is again under controlled setup without cosmic ray contamination, and you can look for indirect signatures, detection signatures of dark matter, direct signatures of dark matter, baryon, scattering, or third, you can look for indirect signatures of dark matter through astrophysical observables. So this is basically what I will be focusing on. I just mentioned one, which is essentially self-annihilation of dark matter. If you allow dark matter to interact non-gravitationally, then it may couple to essentially modes that we know in baryonic physics and produce gamma rays and other leptonic high energy particles that produce showers that are detectable through such high energy observables. But I will be focusing on strong lensing. So just going back to the more almost traditional way of weighing galaxies, I will go back to that, but make a case that we can take that idea to an extreme where not just being sensitive to macro lens model, but also being sensitive to substructure within it. Now you might ask, why do you care about substructure? Because if you want to discover dark matter and understand what dark matter really is, we need to understand how dark matter clumps at small spatial scales. This is because in Lambda CDM, Lambda Cold Dark Matter paradigm, which is the standard model of cosmology, structure essentially builds starting from the smallest scales through mergers and accretion, builds larger and larger clumps over time. And this is a hierarchical and ongoing process, which means that if you stop the simulation at a particular time, then you will always get a residual amount of substructure that has not yet been tidally dissipated or otherwise accreted into a larger halo. We call this substructure, subhalos. So every halo that you will see, eventually, even the largest ones that may not necessarily have been gravitationally relaxed, will have some fraction of their mass locked up in subhalos. So in this sense, subhalo is any very gravitationally bound structure within a larger structure. So in cold dark matter simulations, the virialized equilibrium distribution of dark matter is described by the NFW profile on the right. So this is basically some scale density. Then as you can see at short radii, you have a 1 over r dependence. At large r, this becomes 1 over r cubed dependence. If you square this and project it on the sky, you essentially get a prediction for what the mass line of sight density should be. And you can also generalize this for subhalos. This is not shown here, by multiplying this by a factor that goes like some truncation radius squared divided by 1 plus that truncation radius squared, which then allows you to truncate the mass density beyond certain radius, which is required through simulations, because as I mentioned, this is an ongoing process, and the larger structures are always trying to accrete the smaller gravitationally bound structures within it. So the smaller ones are always subject to tidal dissipation and evaporation. So their velocity dispersion, because of the tail of the velocity dispersion, they're always losing mass to larger structures. Because of that, we have to take that into account in our prediction for what the mass distribution should look like. On the left, you see the concentration-dependent density. So my single point here is that the concentration is unknown and probably remembers, which is an outcome of the n-body simulations, the concentration of a subhalo remembers the average density of the universe when it collapsed. So every subhalo is a function of redshift over cosmic time, will have a concentration that will remember and potentially trace the infall redshift. So with this knowledge, you can say, well, okay, I think I understand how the universe behaves at these short, small scales. So you can paint your, I guess, hypothetical or mental understanding of what the universe should look like on your simulations. And this is basically what you get. At the center, you make the prediction that as you get to smaller velocity dispersions, which means smaller masses, you get this rise of subhalos or their abundance. And basically, this creates a mismatch between what we can see around our Milky Way. Because our Milky Way while it does have certain satellites, it absolutely does not have the number and concentration of those satellites to match with this type of prediction. On the right, you actually see this in an image, how that looks. Now, what I just described can be described in two very concise problems. One is missing satellites. Where are all the satellites? And the second one is, in addition to being absent, the ones that happen to exist, they're just not massive enough to actually hold on to their stars. So we have a twofold problem here that needs to be solved, especially in our local neighborhoods, considering our galaxy. And can we find essentially observables that can allow us to attack this problem? When I was driving this morning, by the way, from St. Louis over here to Urbana-Champaign, I actually realized I was just maybe a little sleepy or just had too much fun. I realized we also have a missing satellites problem here, because St. Louis area seems to not have any large number of like metros just next to it. So this also, to some extent, feels like unnatural, because normally you would expect a halo to have smaller halos next to it. So I took this route to Urbana-Champaign. I just saw this little town here, and I think that was where you said the cross was. Other than that, I did not see any substructure. So what is this gravitational lensing problem? I already introduced it. Let me just show you the idea with just one slide. So in gravitational lensing, the problem geometry is such that you have a source plane and a foreground or image plane. So the source plane is where normally you would see everything in the absence of the image or foreground plane. But because of the mass distribution in the foreground plane, which introduces a so-called deflection field as shown with the alpha vector field here, then you essentially see everything at theta instead of beta. So at the top here, this is the so-called lens equation. Lens equation just basically says that your image plane is related to your source plane through an additive deflection field. That deflection field itself depends on your mass distribution through what we refer to as convergence and shear. The shear itself comes from typically the external large-scale structure, so it's not local, but the convergence is due to either the main halo or the substructure around it or the line of sight halos. But those three components together add up to construct a kappa, the convergence field, and basically by integrating that, you get the deflection field, which then acts upon your original coordinate system to map them into your image plane. So using this, one reminder though, when I say lensing, you might immediately make a connection to lensing that you know. For example, the optical lensing from refractive surfaces. For example, if you just take an ordinary lens, you can make it such that that ordinary lens is going to have a focal point. Gravitational lenses do not have focal points. They have focal lines, which means that depending on the impact factor, the distance to which you are going to focus your light will change. So you cannot just find a point and focus all your light to it, which also means that you have to be very careful about your deflection field, because it's going to change as a function of your galactocentric radius, because of what I just said. But other than that, it's a very similar problem. You have a deflection field, you take into account your mass distribution, you predict your deflection field, you forward model, do ray tracing, and then forward model what the brightness distribution will look like. There is a mass sheet degeneracy, which I will have to skip or not discuss in detail, but there are certain degeneracies involved because of the way gravity works. But once you take these into account, which means essentially you need additional dynamic constraints on the masses, once you have that, you can actually break the degeneracy between the main halo and the subhalos. But you will still need some additional mass constraints because of the degeneracy. On the left, you have the geometry example for the sun. This is basically an outcome of gravitational, general theory of relativity. In fact, a very famous confirmation of that came in 1919, sorry. And the same idea is applicable to strong lenses. On the right, you see a more recent survey from Adam Bolton. This is the SLACS survey using HST on targets that were pre-selected using SDSS spectra. So they basically looked at SDSS spectra, tried to predict which galaxy have two lines, and then pointed HST at them. And the outcome was essentially discovery of over time, hundreds or so galaxy type lenses that now constitute our golden set of what these systems actually look like. This is again HST work and a while ago. Now, coming back to sub-galactic scale, so you can play the same game by not just having a foreground mass, what I typically refer to as macro lens model. It's just jargon. It just means that you have a smooth mass distribution. We call that the macro lens model or the main host galaxy. I think they're all interchangeable in this context. You can start adding mass to this smooth halo or smooth mass model, but only at a level that is not going to change your Einstein radius. We call that perturbative addition, because if you add an entire new galaxy, that changes the entire problem, because that's not going to be perturbative. It's going to change your Einstein ring. It's going to modify it. Because the Einstein ring, by the way, is sensitive, only sensitive, in fact, to the total mass within the Einstein ring. So by adding an entire new galaxy, for example, you'll be disrupting that assumption. But if you only add subhalos with total mass of order a few percent of the smooth halo, then your Einstein ring will not move because you're just adding a percent level mass. Instead, the multiple images that have been produced around the Einstein radius will change their fluxes, not their positions. I just want to highlight that point because typically the astrometric perturbation is of order a milli-arcsecond. That is why, in fact, we call this milli-lensing. It's also known as milli-lensing signature. And even in space-based photometry, leave alone seeing limited photometry, even in space-based photometry, you can't distinguish astrometric perturbations of order a few milli-arcseconds. The best we have right now is HST in the blue passband, and you can't really do milli-arcseconds with that. So despite the fact that the image is actually moving by a few milli-arcseconds, the observational consequence is that it doesn't move at a level that you can detect, but the flux is changing. So what's happening is essentially you modify the fluxes of your multiple images. This is the signature introduced by subhalos when you add those subhalos to your mass model. So this has been essentially proposed and demonstrated to work almost a quarter of a century ago. And one of the first works was Daylan 2002. And there they essentially showed that you could actually constrain by taking these subhalos, individual detections, to constrain what they refer to here as FSAT, which is essentially the fraction of mass locked up in satellites or subhalos. that you can actually get a constraint on this number by individually taking into account the fluxes. Now, more recently, this was my second PhD project. I worked on this to produce what I referred to back then and still as transdimensional gravitational imaging. Now, what I just described of taking a strong lens and, like, for example, as it looks here, here you have 3 images and a central host galaxy. Taking these images and modeling them based on your understanding of the mass model is called gravitational imaging. It's a fancy name. Obviously, it's just playing on the word. You're imaging so-called gravity because you're imaging essentially the mass line of sight projected mass distribution. Now, here the difference was that in my approach, we approached it using hierarchical and transdimensional Bayesian methods. The idea was that the subhalos could be essentially killed or added to your model in a way that respect detailed balance when you're sampling from the posterior. This has some literature. I mean, we called it, in my PhD thesis, I called it PCAT, probabilistic cataloging, and applied it to many other problems, not just this. But actually, in the statistics literature, it's an older idea and has a distinct name. It's called RJMCMC, Reversible Jump Markov Chain Monte Carlo. So it has a literature footprint that's older, but we basically just almost relabeled as PCAT for astronomy. So we developed this method, and as I mentioned, I will skip these details. It's transdimensional, Bayesian, and hierarchical. So we had both within model proposals that you would probably be all familiar with from your favorite sampler, at least those of you who are doing modeling. But then we added burst stats and splits and merges. So those are the transdimensional components. In order to not derail the topic too much, I'm going to skip the kind of the technical details of the sampling, but if you have questions, I'm happy to talk about them later on. So using this, we showed that we can, similar to Dalal and Kochenek, we could actually constrain the FE sub, which is the same quantity. This is the truth value, and these are my percentiles. We could essentially constrain the same quantity. On the left, you see the projected mass density, again, as along the line of sight, and green is the truth. So you can see that our projections are aligning nicely with the subhalos that are the underlying truth, but not 100% as it should be because of the large swath of degeneracies in this problem. But it was definitely doing much better than traditional because on the left you have the traditional modeling. It's fixed dimensional. You take either 0 or 1 subhalo, and on the far right, these are residuals. So the closer you are to 0, it's better. So we demonstrated that we are essentially on average getting a much better agreement between data and model. Anyways, so this is still a few years before, so I will skip these. Oh yeah, sure. So the fluctuations of the truth field. Yes, so on the left, so this basically shows the model posterior median minus the data. So the more deviation you have, the model is essentially making a worse choice or worse conclusion. So the reason why this happens is because in the one subhalo case, the model is essentially reconfiguring its macro lens model to adjust for the absence of the additional subhalos. That's why you basically get purple all around. So you're essentially making a systematic error. Here, we can't get the cores of the other subhalos because they're away from the multiple images. So here, the multiple images are here and here. So you can't hope to get all the subhalos because this is a really tricky problem. You're absolutely not sensitive to anything that is far from your multiple images.
The X's are the subhalos in the model to begin with, or the ones you've extracted?
To begin with, they're the truth. Yes. Okay, so let's move on to Roman. So yeah, we are halfway through, which is great. So we will talk about Roman and what it really means for this problem. So once I was done with my PhD, I spent a few years working on exoplanets, which I still do. But over that period of time, I continued to work on Roman, kind of started to keep an eye on its capabilities. And while Roman, as a historical design fact, it's been optimized for and mostly advertised for weak lensing, it is also going to have a transformative impact on strong lensing. And in fact, with the new paper that we just submitted, we are trying to basically make a case for that. And that's what I will also cover for the remaining of my talk. Just to set the stage, in order to make advance in this field, in this particular problem of finding subhalos in these lens systems and then convincing yourself that they're real and that such detections or non-detections actually mean anything for cosmology, you need a few things. First, you need many of these systems because of what I just described. If your subhalo does not land close to your multiple images, then your perturbations are going to be too small, which then means that your cross-section of getting a relevant strong lens is really small. It's in fact smaller than the Einstein area of the strong lens because most of the time your subhalo, the most massive one that you can hope to detect, will actually be out in the middle of nowhere, not close to your not close to your multiple images, and that's going to not be useful for constraining or testing cold dark matter. So that means in order to really get one robust detection, typically you need tens of such systems with high signal to noise, where you can say, I've repeated this experiment 10 times and I've detected zero. Therefore, it must not exist. Before you do so, before you get the trials factor in your favor, you can't really make that statement. So that makes the case for wide field of view. Second, we need infrared capability because we want to start moving a little farther out into higher redshift. Because we, unfortunately, with strong lensing, if you're just restricting yourself to lenses and sources that are at low redshift, then you have, again, the cosmic variance, like you don't have enough samples to work with. So you want to be able to push to higher redshift, which means infrared. JWST can certainly do this, but as you probably all appreciate, it's hard to get time on JWST. It's not a survey mission. Hence, going back to my wide field of view argument. And most important of it, you need high resolution. This is not an experiment you can do from ground because of seeing limited photometry. But even in space, you want angular resolution that is going to allow you to distinguish these multiple images, separate them from the brightness of the host galaxy, the one in the foreground. The one in the foreground is also bright, don't forget. So basically, you need to be able to separate your multiple images from that. So you need three things: wide field of view, higher angular resolution, and infrared capability. You don't need spectra for this. So for example, as maybe a follow-up point, good imaging data is enough to construct good lens models. You will eventually need some spectra of the system, which can be collected from the ground, to break certain mass degeneracies, but that is not a prerequisite to get a good mass model. And this is Roman, by the way. Okay, so a few weeks ago, my team and I attended the HLWAS meeting, and we were very fortunate to actually get a tour of the clean room from outside. So on the right, you actually see Roman as it is now in the clean room. So we are all excited. So wide field instrument, which is the instrument that we will use to do this imaging, is actually on the right back side of this here. And you see the spacecraft bus, most of the primary mirror, etc. here. So and it's going to have 6 struts, unlike HST. So the PSF looks a bit different. You'll see soon. If you go there, it's really fascinating. We also took a picture of the wide field instrument. It's here. This is my photo of it, and this is my grad student who has been working on this project with me. So this is wide field instrument over there. So wide field instrument is a fascinating instrument. It's a really big area of CCD that's going to be the prime instrument for Roman. But Roman will also have a coronagraph, and Roman will also have a grism and a prism for the wide field image, although our science case uses the filters, the broadband filters. So we are not using the grism or the prism. So on the right, this is just as an introduction, what one of these strong lenses will look like in Roman. We just simulated that as part of an ongoing work. This is an arcsec. Here you see the orange dot shows the location of the source. Blue one, the blue line is what we refer to as the critical line. The caustic is shown with the green contour there, and red one is actually our lens or lens galaxy. And on the left, you see now in different filters for Roman as well as different filters for LSST, HST, and Euclid, the same system. As you can see, Roman is not like uniquely the best instrument to do this, but it certainly, because of its wide field of view, it is uniquely suited to finding and characterizing the highest number of such systems, which is critical, as I was mentioning. And on top of that, while HST could do this, it is not a survey mission, so it will not allow us to detect and characterize 1,000 of these systems. And so nor will JWST. And LSST, unfortunately, is seeing limited. There's a lot of very interesting science you can do with strong lenses, which I'm happy to talk about, but that's not the main focus here. And Euclid is very interested. Its data is going to be publicly released very soon in a few months, and we are looking forward to working on that as well. But it is only going to be a precursor to what Roman will be able to do because of its limited effective area as well as PSF. Now, just going back a few years, when Roman put out the solicitations for community feedback into what the core community surveys should look like, my colleague Simon and I basically responded to it with a white paper that essentially set the stage for what this is going to look like in the Roman era. So here we made the prediction that about 500 such Roman characterizable lenses will be discovered. And the blue one instead is the total number of Roman detectable lenses that we predicted, whereas the red one is the underlying simulation here as a function of red infrared source magnitude. And this was a very crude, rough estimate that we did based on the model and Gaussian galaxies that we had at the moment, not taking into account any Roman systematics. So this was a very crude estimate, but we basically used it to argue that the high latitude wide area nominal baseline mission is not going to be enough for us to detect and characterize enough of these systems. So here, for example, you see the high latitude time domain survey here, the high latitude deep survey that we basically proposed, and the high latitude wide area survey here. This is a trade-off space. So you're trading off survey area with exposure time. Now, obviously you want a higher survey area because that's the only way to detect enough systems. But then going too wide will then cause the survey to be shallow. And we basically made the point that if you just take the high latitude wide area survey as is, which is just 4 exposures of about 150 seconds each, then it does not give you the SNR per system that is required to detect individual subhalos in all of them. So with this, we basically argue and still think the same, that we need basically either a guest observer program or a new program that's a little deeper than the high latitude wide area survey in order to really gather a statistically complete but deep enough set of exposures on strong lenses. So in the second iteration of this work, this time led by my graduate student, Bryce, we started revisiting the problem more recently with a bunch of collaborators, this time more collaborators, revisiting the same problem of strong lensing with Roman, and came up with a pipeline that we call Majira. If you want to take a look, you can do so. We just submitted the paper, and it will be on archive and after acceptance soon. So the idea is that now we are making the case that, yes, high latitude wide area survey is going to be transformative on this problem. As you can see on the left, the total amount of time that will be spent on exposing on those strong lenses is going to be almost an order of magnitude larger. And this is taking into account all of the surveys that HST essentially did, such as Castle, Slacks, SL2S, and Bell's gallery. So the total amount of time spent on strong lenses will be much higher, but it's still not going to be as is again. Not going to give enough strong lenses that may be needed to solve this problem once and for all. So we are still arguing that potentially deeper surveys may be necessary. In this work, we this time, more recently, took into account all of the known Roman systematics. So Roman, before it was, now it's in integration mode, but before that, they actually tested wide field imager and they produced many cycles of test calibration data. So we used those. We used basically all known sources of nonlinearity and all the corrections, the dark current, it's the readout noise, etc. And the reciprocity failure, as you can see, which is essentially going the opposite direction of the nonlinearity. So we took into account all of these. And then we also took into account the different 0 points of the 18 silicon chip assemblies that you can see. This is the focal plane coordinate system of Roman. So here we are showing, for example, the PSF evaluated at this point here in CSA 04. So you can see the PSF over there. This is basically the radial profile of that PSF. This point happens to be the point where the Zernike coefficients in quadrature sum is actually minimized, which means optical aberrations are smallest in this focal plane because it happens to be close to the coronagraph where they want that property. Whereas if you go, for example, to SCA 17, that is no longer the case, and you get a growing Zernike coefficient. So we also computed the residual of what the PSF looks like at different points. So as you can see, we start to pick up some asymmetries as we go around the field-dependent PSF changes, and we want to take into account in our PSF, in our strong lens modeling. So we then started simulating systems with this knowledge. As you can see here, the SNRs and the redshifts are all shown. And our definition criteria for substructure amenable strong lenses is such that the lens, the multiple images should be separated from each other, individually detectable, and also separated from the host emission. So with that, we can be confident that the delta chi-squared of adding a given subhalo is high enough that when we retrieve it, it should be a statistical detection. In this plot, in this polar plot, we show as a function of, I guess, 18 SCAs, the contribution from different dark matter scenarios, as well as the systematics involved with each SCA from the field-dependent PSF. And the point of this is that for some of the SCAs, the contribution is even larger than the signal, which means that you need to have a good understanding of your systematics and remove them before you can hope to do the science. And for some others, they're comparable or even better. Then we played the game of adding subhalos, measuring their chi-squared, and increasing their mass until we deemed them detectable and then characterizable. So moving to the right, as you can see, the p-value is dropping, which means the chi-square is increasing. So we did that over the full focal plane. So we got this plot, which essentially is the lowest detectable subhalo mass in units of solar mass. As you can see, this is 10 to 9. So roughly 3 times 10 to 9 is the average lowest solar mass. 10 to 9, 3 times 10 to 9 is the average lowest subhalo mass that we can hope to achieve, which somewhat depends on where we are in the focal plane, with just the high latitude wide area survey again. Please.
From your pie plot, it looked like there was a pretty wide range of sensitivities here, and yet it seems like it translates only into a very small range of masses, minimum masses.
Right. So basically, this includes the effects, but effects can be taken into account, so we can actually understand them and undo them. Yeah. So one point about how this is going to look in different core community surveys. As I mentioned, Roman is going to have multiple core community surveys, high latitude wide area survey being one of them. The other one is going to be essentially a much smaller, again, high galactic latitude time domain survey. And that's going to have a few square degree of order, a few square degree footprint. So as you can imagine, it's going to be cadenced in order to find lens quasars, etc. And we predict that actually the contribution to the lowest detectable subhalo mass will be mostly from those, and which makes sense because you'll be able to co-add them and get much deeper images, and they will actually allow you to go much deeper or smaller in subhalo mass. The issue is they will only be producing just a handful, probably 20 to 50 or so strong lenses amenable to substructure characterization. And this goes back to the original point that the HST itself, while being able to do this with long exposures, was not sufficient to solve this cosmological variance problem, in the sense that you're not finding enough systems where you expect the subhalo to be close to one of your multiple images. So my point is that while the high latitude time domain survey, being much smaller footprint and deeper, will allow us to detect strong lenses with potentially smaller substructure, they are not going to give us the statistics necessary to address this problem. Whereas the high latitude wide area survey, or just a little deeper version of it, will essentially allow us to do that. This is not to undermine obviously the science potential of the high latitude time domain survey. It is going to actually give us golden examples of what these can look like once we actually figure out how to dither and actually produce simulated images of these strong lens systems. Once we dither, for example, 60, 70 exposures, we will get a much better effective PSF because we'll have sampled the PSF at many points. And we are currently working on that because it is currently unknown exactly and how optimally that's going to happen. We left it outside the scope of this current work, where we actually focus on the systematics of Roman, but subsampling of the PSF and over resolving in order to actually get much better PSF is also part of this enterprise, and we are currently working on it, in case you were wondering. Okay, so this basically plot shows then a strong lens image, again sampled at this edge, the lower right edge of SEA4, and 4 others that have the same system, but evaluated at a different focal plane point where the PSF is a little different. So we are basically demonstrating the difference. And the power spectrum of these essentially went into that polar plot that you just showed, that I just showed. By the way, we get this image using STEPS, which is a Roman software. So let's sum this all up and produce a few numbers, because we've shown a lot of images. Now let's talk about the yield. Now we predict about 93,000 detections over the full high latitude wide area survey, assuming a nominal roughly 150-second exposure. A single one, though, because the nominal high latitude wide area survey is supposed to have 4 of them. But because we wanted to separate out the complications of dithering and supersampling the PSF, instead of trying to make a potentially biased and wrong estimate on that more complicated quantity, we basically chose to report the yield based on a single exposure, which again is I mean, at face value, you can just multiply it by 2 because the signal to noise will go like the square root of the exposure time, but it's not exactly going to look like that because the PSF is going to improve at the expense of slightly suboptimal SNR dependence. So if you have more questions about that, I can address them separately. But so we basically make the predictions on quantities that are more agreeable with others. So again, just repeating, we leave out the super sample PSF aside, and this is for a single exposure. Now we predict about 90,000 strong lens images, and only 500 of them in this single exposure case will have SNR greater than 200, which we think is necessary to detect individual subhalos of order 10 to 9 solar masses. And 500 is a great number. I'm not going to say, it's not going to be sufficient, but with essentially contribution of the 4 dithers and potentially a little deeper survey, we could actually get over 1,000 very easily. And that is then going to be a very interesting number because then you will essentially be able to, maybe as a function of redshift, have bins with individual statistical power to say, well, a non-detection actually means anything because you will have, again, many systems through which you repeat that experiment. Although one thing I have to say is we did not simulate the entire high latitude wide area survey footprint in this single paper because it would be too much. In fact, the high latitude wide area survey footprint is about 2,000 square degrees. We only simulated about a quarter of that. Sorry, actually, no, 1/7 of that. So that was just to make this a little more computationally accessible. But we just rescaled everything to match the high latitude wide area survey.
Is the length of these surveys limited by cryogen or something? Or is there any reason why you can't just, go back for more time?
So Roman does not use cryogenics to my best knowledge. So it would not be running out of that. This is all based off of the baseline mission, which I believe is 5 years, and people hope it's going to be 10 years. So that 5-year is typically broken down to community surveys and geo time. So the community survey time dedicated to the high latitude wide area survey was nominally 24 months. And only about 1 year of that is actually only for imaging because the rest is for GRISM and PRISM. So if you just do the math, there's a natural, boundary within which you can just do homogeneous imaging in these 4 passbands.
A new survey.
Yeah, absolutely. And just to add, this is the core community survey. There's also going to be computed time, geo time, where people will actually be able to propose to support their science cases, which may include more imaging of the same fields.
Where are Einstein rings? That should be 1, right?
Which one?
Number of images, Einstein range was 1, or am I reading that plot right? Where
you mean this one?
Yeah.
Well, I mean, we don't have 1 image ones because we can't do substructure studies with them, so we just discard them. No, so if you treat like a perfect Einstein ring, that would be 1. But typically, in reality, what you get is things that look like an Einstein ring, but usually get 2 images. So like you basically have a numerical game there. Like you never get exactly 1. Even though it looks like a ring, typically you get 2.
Yeah.
More questions? Right. So here you also see, just for comparison, the SLACS SL to S Bell's gallery, again from HST, the or the orange and the red ones, clearly this is going to be transformative. We will get order of magnitude in improvement in our ability to detect and characterize them. And as you can see, we rely heavily on multiple images, and our cut for characterizability is over here at 200 SNR. For SNR, by the way, we use a specially designed mask. So we basically optimize our signal to noise and only sum the signal to noise delta chi-squared within certain pixels. That is based on our model of what the host galaxy looks like, as well as what the macro lens model looks like.
So are you doing, like, for the signal noise, are you accounting for the lens and like removing it somehow before you do the signal noise?
Yeah, so we basically, based on our understanding of what the macro lens model looks like, we basically select a subset of pixels, because you don't want to select pixels where there's too much contribution from the foreground host. Yeah.
And how are you dealing, have you accounted for line of sight?
Yeah, that we haven't and is on our to-do list. Line of, again, the point of this paper, this is ongoing series of works, but in the one that we just submitted and will be on archive soon, that one does not include the line of sight halos, because we want to separate out the effects in order for it to be more comparable to other works. But the pipeline itself will eventually have the Majira pipeline will eventually have line of sight capability. Yes. And this plot is just to show you basically the time complexity. So we have been exploring ways to make this a little faster. We essentially use super sampling wisely, so to speak, to keep the computational resources needed to do this manageable. So typically to produce 10,000 images or so, we just need a few hours. So that's been very manageable. Okay, so we predicted about 93,000 detectable strong lenses in the high latitude wide area survey. Again, as a reminder, one exposure only, no dithering, of which about 500 will be sufficient high signal to noise strong lenses that will enable detailed substructure characterization. In the just few minutes I just want to show a few slides. One is about access. So access just basically passed phase A. Some of you may already be familiar with it. Otherwise, access was one of the responses to the solicitation for a probe class mission to NASA's response to essentially Astro 2020. And now, along with us, Prima got selected. So the two teams have been given go to advance their technology development and demonstration. So right now, the team is led by University of Maryland, Chris Reynolds, and we are. I'm only involved in the science case development and our science book right now, but the team at Goddard is currently developing a tech demo that's going to try to demonstrate to NASA that this is essentially how the next decade of astronomy should look like. Here, I'm holding one of the mirrors that were produced essentially as a demo here. So once we have 18,000 of them, they'll basically go produce concentric circles, and we'll have a 1.8 meter diameter mirror that's going to constitute access, which is essentially Chandra, but with a much wider field of view on the same theme, I guess, as Roman, as compared to HST, but also with much better effective area, because Chandra's effective area, as some of you may know, has been slipping, unfortunately. One other thing, today I mentioned ExoCore to some of you. I just wanted to include a QR code in case anyone is interested. If there are any grad students or postdocs who want to get involved, contribute to ExoCore. Some of you will know what I'm talking about. It's essentially one of a component of NASA's transform to open science. If you're interested in contributing to open science, especially in the context of exoplanets, you can even come talk to me or send me an email, or otherwise follow the prompts. One other thing, soon we will have the 50th anniversary symposium at McDonald Center for Space Sciences at Washington University. So if you're interested in giving a talk and MCSS WashU is pretty nearby, as I can attest to. It's a 3-hour drive. This morning I took it. It's pretty good. So if you want to drive down to give a talk, you can submit an abstract to this call for contributions. And in general, if you're interested in opportunities at WashU, we have postdoctoral fellowships, graduate fellowships. You can come talk to me or other faculty of interest at WashU. With that, I'll just take any questions.
You talked a bit about using this technique for galaxy images. Does your forecast have a breakdown of like how many multiply image quasars we could possibly see with Roman?
Yeah, so we did not do quasars, and the reason is for the substructure problem, you want structure in the foreground. That allows you to have a larger. So I talked about the fact that you're fighting against cross sections. It's a cross section game. In the foreground, you want as much area that essentially constitutes a multiple image as possible. So that's only possible when your background galaxy is a fluffy early, galaxy. That's a young galaxy, potentially even irregular. But typically we get these like spiral galaxies in the foreground that are really blue. So those, when magnified, will produce much larger multiple images and will give you a larger area over which you can play the detection game. Quasars do not. So as a result, we did not simulate. I mean, for this specific case, although there will be a lot of quasars that will be discovered with Roman.
So with all the detection Roman, what cosmological parameter you constrain the velocity of the dark matter, right? Are there the equation of state or what?
Right. So for this science case, the parameter that you're interested in is essentially the fraction of the mass fraction that is locked up in halos in the form of substructure. That is a number, and typically lambda CDM predicts that to be about 1 to 2%. So we want to constrain that observationally. Yeah, so we right now, I mean, based on previous work, I know that like this is not the current paper, but we know that order 1,000 systems is going to do it. So the question is, can we actually get 1,000 systems with large enough, high enough SNRs with controlled systematics?
Any questions online? Okay. Last call question.
Does constrain that parameter do you solve some of these tensions, like the same that you mentioned, or like do you get a good omega matter?
Yeah, so sigma 8 is basically a large scale structure issue. So it's at much larger scales. So this science case is mostly focused on the small microphysics of dark matter. So that while there may be a connection, we can't just use one to infer the other. It's almost an independent measurement. So you can certainly do that type of work using strong lenses, because strong lenses also, I've given a very specific talk here because there's a lot of other things you can do with strong lenses. For example, measure the line profiles too. And some of those larger scale observables can actually be sensitive to equation of state and even other cosmological probes. Yes, please.
Following up on that, I mean, so presumably you could constrain the dark matter self-interaction, dark matter cross-section. Yes. Can you do better than existing one?
Right, exactly. That's the point. Right now, I mean, in previous work, we demonstrated that we can certainly do rule out fuzzy dark matter. So fuzzy dark matter, for those of you who don't think about that, if you basically get wave-like dark matter and the mass of that is essentially somewhere in between 10 to negative 22 and 10 to negative 19 electron volt, then the de Broglie wavelength of the dark matter is going to be between a kiloparsec and about a parsec, in which case it's going to start erasing substructure, primordial substructure. So we can start to rule out if we have enough systems and we keep not finding such subhalos, then we can start to rule out fuzzy dark matter. For self-interacting SIDM and warm dark matter, probably in the same class, but SIDM, that's SIDM is somewhat degenerate with baryonic feedback. It's just a little hard occasionally to just single it out and be able to just constrain that separately. But there's work that shows that SIDM could also be independently constrained.
Any further questions? Okay, let's take our speaker.
Thank you.